Okay, good afternoon to all. Divagar, are you there? Register number 28, Divagar. Please unmute and speak. Divagar, register number 28. Please unmute yourself and speak. Divagar, Divagar, register number 28. Divagar, where he went, someone please join. He is in meeting. Mic not working. Simply saying mic not working. Yeah. So just unmute yourself. Just unmute. We will check whether it is working or not working. Just click the button. Uh, Darshan, are you there?
Yes, sir.
Okay, what about Divagar? Okay, Darshan, the question to you.
Sir.
Darshan, what we discussed yesterday? So what are the topics we have discussed yesterday? What I think you have take home points from yesterday class. What are things we have discussed yesterday?
Polarization, sir.
Okay, next. Polarization. Okay.
Refractive index.
Okay, refractive index. So what is refractive index? A simple word. So what is the formula? How we can calculate the refractive index? So what is the formula for refractive index? Or how you are denoting the refractive index?
N equal to
Hello,
C
sir.
by V, sir.
Wait, both Darshan and Divagar, please unmute yourself. Both you can answer. Divagar, tell me what are the things you
Sir,
have learned yesterday class?
yesterday, sir, refractive index, Snell's
Okay,
law,
okay.
polarization,
So that's why we are going to discuss, but I think we have discussed outline. Okay, done. So what is the
uh,
formula for refractive index, Divagar?
uh, like speed of light in vacuum by speed of light in medium.
Okay, super. So denotation for that is how you are denoting refractive index, Darshan?
Sir,
N
How we are
equal to
denoting?
C by V, sir.
Okay, super, super. Thank you, thank you. Please
thank you.
mute yourself. Thank you, Divagar, and thank you, Darshan.
Thank you, sir.
Okay, done, done. Thank you. So that is the thing. So we have discussed refractive index and polarization characteristics and the basic ray optics principle. How are the signal? What is the classification? Either incandescence and luminescence. So basic characteristics we have discussed yesterday. So finally, where we stopped means refractive index. So refractive index n equal to c by v, as Vivek said and also Dawson said. N equal to c by v. C equal to the speed of or velocity of light in your normal space, or then to the velocity of speed into the medium, or in a vacuum or in a medium. So that is the idea behind the refractive index n equal to c by v. Someone please, if you know the answer, please put in a chat box. What is the refractive index n value for air and water? What is the value of n for air and the water? Okay, 1 for air and water for 1.33. Very good, Aarti. Thank you. So refractive index for air is 1 and the water is 1.33. So that is the idea. So we will go to the next one. I will present my screen now. Wait a few seconds. Okay. I think now it is visible. Is it visible? I hope is it visible. Okay. Someone please. Okay, done. Thank you, thank you. So this is idea. Refractive index for air is 1 and water is 1.33. Okay, super. So refractive index idea is to identify what is the parameter of n. Then based on that n, how the light signal is reduced into the medium. So those things we can understand by the refractive index. So one more thing already we have discussed. Based on that, we can see here by optical you can see, yes, this is the idea. Either optical, by the help of optical geometry, you can explain the light propagation. By the electromagnetic theory concept, you can understand the spectrum. By the photoelectric effect, you can know the basic characteristics of lasers and photodetectors. So we have to know basics idea about the optical geometry to understand how the light signal is going to into inside the fiber material. That is the thing we are going to discuss detail in our upcoming sessions. So that is idea of refractive index. So refractive index, by the help of optical geometry, you can understand that the light is nothing but your ray. The light propagation, normally it is a homogeneous medium or in a generally optical system, optical fiber material, it will be in a straight line. So we have a two diagram over here. One is refraction, another one is reflection. In any medium or any signal, light from moving from one medium to another medium, here I am denoting that N1 is a medium 1 and N2 is medium 2. 1 and 2 denotes medium 1 and medium 2. N1 denotes refractive index profile, that is RI profile of medium 1, and N2 is RI profile of medium 2. Generally, the N1 N2, we have a obviously we have a two medium. When you are inserting from light source to the other fiber material, definitely it is a medium 1 and medium 2. Or generally, if it is a air medium to the glass material, or if it is a air medium to the water material. So that is the idea behind the normal principle behind the light propagation in the optical system. So N1 is RI profile of medium 1, N2 is RI profile of medium 2. Okay. And one more condition before going to understand the basic principle behind the optical systems, N1 value should be always greater than the value of N2. Or simply I can say N1 is greater than the N2 always. You have to ensure that the N1 value should be higher than the N2. Then only the maximum optical signal or maximum amount of information will be transmitted to the your optical fiber material. So this is a N1 and this is N2. That is the basic characteristics. N1 should be greater than the N2 always. That is the main thing. And you can see in any medium, it is a wired or wireless. You can understand that when you are inserting any light or when you are transmitting any information into the medium, definitely some amount of energy will be refracted to the other medium. That is one medium to another medium. Some amount of energy will be reflected back to the same medium. That is the basic characteristics in a normal light propagation. The same thing we are going to discuss in our refractive index also. So in this diagram, we can understand this is the refraction and this is a reflection. So refraction, when suppose it is a medium 1 and medium 2, I have conveyed that. So this is I denotes the incident signal or incident ray. You can see this light always be rays. So wherever I am speaking about ray means it is a light. So incident ray and this is R denotes the refraction ray. So incident ray with respect to the normal line or with respect to this interface line between N1 and N2, you can understand that it makes an angle with respect to the normal line. It makes theta I. Theta I incident angle theta. Then based on the characteristics of N1 and N2 are the medium 1 and medium 2, some amount of energy, I told the some amount of energy is reflected back to the same medium, as amount of energy will be transferred to the or transmitted to the other medium. That amount of signal is called by the name of refraction. So you can see here, this is incident ray or incident light signal. it makes a theta I with respect to the normal line. Then you can see this dotted line with some amount of energy will be reflected back to the same medium, and this brown color indicates that some amount of energy will be refracted to the other medium. So we have to ensure that normally in a normal optical fiber system we have a core cladding. Maybe a next slide or maybe and up to the next slide you can see core cladding. Core is the main area. Core area is used to transmit your light signal. Cladding is used to protect your core. Then we have a buffer and jacket, also the other material which is used to protect your normal the inside the core material. The core material thickness will be the hair thickness. Generally, the fiber material is made by the either glass or plastic. So generally, if it is fiber is made by the glass material, the thickness will be your hair thickness, like micrometer. There's 15 micrometer or 16 micrometer. So generally, it is the thickness will be the micrometer. Just think about, and the hair thickness. This is a micrometer. Inside that, if you are transmitting the light signal, what are the things you have to consider? That is that is the imagination you have to maintain. That is the imagine you have to do. Inside the hair thickness, is that is the core. I am telling that that is not of a fiber material. That is a core size of generally which we are using in our optical system. So that is idea. Obviously, it is a micrometer thickness. Generally, if it below between 15 micrometer or 60 micrometer range, will be difference based on your application. So generally in a micrometer. So this is the area. So I have to we have to check that this is the incident signal with respect to the your interface line between N1 and N2. Suppose if I am taking N1 is the air medium and N2 is normally water or maybe glass or some other principle. So N1 and N2 we have to check the N1 should be greater than the N2 always. If generally if I am speaking, I just I consider this is N1. Sometimes inside the core material, if you are speaking about this N1 and N2, I am telling inside the core material or inside the fiber material. Inside the fiber material, the N1 based on the core and N2 is based on the cladding. But generally, in a theoretical value, if you are discussing, the N1 will be the air medium and N2 will be the other medium which we are going to transmit the information. But inside the core or inside the fiber material, the N1 is core and N2 is cladding. That is the thing you have to differentiate between core inside the fiber material in general definition. So this is the idea of refraction. You can see this diagram. This is incident angle or incident light wave with respect to the normal line. It makes an angle of theta I. Then some amount of energy will be reflected back to the same medium. So that is reflected signal. That is CR. This is refracted signal. That is C capital R. So this is the difference between the refraction and the reflection. You can see here, this is the formula normally. Basically, you know the basic idea of Snell's law. Maybe you have studied in our normal basic physics. So N1 sin theta 1 equal to N2 sin theta 2. That is the normal formula. Generally, N1 sin theta 1 equal to N2 sin theta 2. Sin theta 1, theta 1 and theta 2 is theta 1 may be the incident angle, theta 2 may be the refracted angle or reflected angle. That is the thing. You can see here, this is the formula N1 sin theta 1 and N2 sin theta 2. So it makes an angle with respect to CI and with respect to angle that is CR. So N1 CI equal to N2 CR. This is the basic idea. And you can see the reflection and system. Theta I definitely should be equal to the theta R. So if theta I is with respect to this interface line, with respect to the normal line, it makes an angle is 35. So say for example, particular for this example, if I am taking the CI makes an angle with respect to the normal line is 35 degree. Theta I is 35 degree. Definitely your reflected signal angle will be 35 also. It has to be theta I always should be equal to theta R. If it is not the case, definitely we have to understand that the signal is not propagating properly inside the core material. We have an issue. That means that maybe the signal is traveling from core to the cladding area. As an optical engineer, as a communication engineer, we have to ensure that which suppose I am transmitting or which I am using for optical communication system, we have to ensure that all the signals are traveling inside the core material, not to the cladding. So cladding, if the signal is transmitted to the cladding, that is the loss. So we have to ensure that always the signal is transmitting inside the core. So how we are ensure how we will ensure that based on this principle, theta I is equal to theta r. The incident angle is equal to the reflected angle. So if it is the case, it deals the parameter of total internal reflection, TIR principle. So TIR principle is we have to ensure theta I equal to theta r. If I'm ensuring this parameter, or if I'm making clear in the parameter, definitely my signal will travel inside the core, not to the cladding. If theta I is not equal to theta r, I have to assume that the signal is not traveling inside the core. Some amount of energy is lost. Please wait. Someone is trying to join. I will admit. Okay, so this is the idea of a reflective index. This is normal system fiber type. Either it is a single mode or a multi-mode fiber. We will detail discuss how the single mode system have to be, how the multi-mode fiber they are manufacturing those things, which comes under the end of the first unit. Generally, this is the structure of a single mode system, and this is the multi-mode fiber. I can see here the N1 is the constant value for step index. We have two different concepts. You can see this area, this is single mode and multi-mode. Vertical, we have a C, step index and graded index. So we have a different combination, step index single mode and step index multi-mode. Here we have a graded index single mode and graded index multi-mode fiber system. So that is how we can compare this one particular diagram. So we have a two multiple classifications: single mode step index and single mode multi mode. The graded index single mode and graded index multi mode. That is the concept. So we have a based on this diagram, we can present four type of fiber mid types is available. So for the particular single mode fiber, you can see here this is the core area. The white line denotes the core area, and the black area which gives a parameter of cladding. So N1 and N2. So you can see here the N1 is constant value. If you are taking that graded index fiber material, the N1 is changes with respect to the R. The R is the radial distance of your core material. You can see that the shape of the step index single mode fiber and the graded index single mode fiber. You can see here you have a small curvature diagram. You can see here with respect to normal single mode fiber. In the single mode fiber, you don't have this type of curvature system, but in the graded index fiber, you have a small curvature. That is the thing. N1 should be equal to constant value. You can get this type of structure. If N1 is varies with respect to the radius of your curvature, this is a parameter of graded index. To understand purpose, I am saying that for the single mode fiber, this is a single mode transmission. For a multi-mode system, this is multi-mode transmission. When we are transmitting, particularly this particular fiber diagram gives a parameter of multi-mode graded index fiber. You can see here the signal is not traveling in a like a normal sine wave structure, normal sawtooth wave structure. You can see here the sine wave structure. So whenever signal is transmitted like a sine wave structure, you can understand that the core value with respect to the this particular parameter n1 into with rn with respect to the radial distance of your system. So that is the idea. Either in a single mode or in a multi mode. That is the first thing. We have to classify majorly. You can classify either single mode fiber or multi mode fiber. That is so okay. Either we have another classification based on this the refractive index. We have a step index and we have a graded index. So this is a combination of a different type of fiber material. Either step index single mode or step index multi mode. Either graded index single mode or graded index multi mode system. So this is the idea of your fiber type. If it is the multi-mode signal, the signal will be the inside the fiber material or inside the core. The signal will travel like this. If it is a multi-mode, if it is a single mode, it is only one mode will travel, or it will occupy the entire your core area. So that is the thing of your single mode and multi-mode system. You can see here before going to see how many people can see this GIF picture here. Can you see? Come on, please. Is it visible? Okay, okay, thank you. So we can see one blue dot and green dot and also the red dot. Uh, uh, Generally, with any signal, or if it is analog communication or in terms of digital communication, you have to understand we know the basic characteristics of the velocity. All the signals will be deals the parameter of velocity. Based on the velocity only we are dealing all the, or we are analyzing either it is analog or digital or whatever may be. So generally, but based on this blue and the green and the red dot, you can understand three type of velocity principles. One is you can see here the blue dot moves at the speed of your normal ripples of your signal. That is phase velocity. The green dot moves at velocity at the speed of your envelope of your signal. So that is group velocity. And you can see the red dot, it deals in front, that is a front side or a front velocity of your general signal. If any signal, or it may be a light signal, or it may be a analog, or it may be a digital, or any signal, we have to understand the basic characteristics of these important parameter. You can see difference. Please understand that the green blue dot deals are that it rotates or it moves at the speed of your normal ripples of your signal. That is phase velocity. That you can see the green dot. It moves the speed of your envelope of your signal. Yeah, I hope you know the basic characteristics envelope. Envelope means suppose carrier signal or maybe a higher than the message signal will be called as a envelope. So that is thing we have here, that is group velocity. So when you are analyzing the blue dot, it deals a parameter of phase velocity. When you are analyzing the green dot, it deals a parameter of group velocity. So that is the important thing. Why I am saying this is whenever maybe in a detail into our optical system, we have to know what is the group velocity of your multimode signal and what is the phase velocity of your single mode fiber system. Everything we have to understand that. So already we have discussed what is single mode and multimode. Before going to the next one, we have to know what is the phase velocity and group velocity of the signal. And I already told that the core carries the information that is in terms of light, and cladding is used to confine light into the core. So I already told that core is the main area. The thickness may be the in terms of micrometer, but it's the like your hair thickness, and the hair yeah, that is your optical fiber core material will carries the information that is in terms of light. Then the cladding is used to protect our core material, and also it confines the light into the core material. That is the core cladding is ensuring that all the light signal is reflected back to the core. That is the idea of the cladding. In order to protect light, in order to propagate the light signal, we have to ensure that the core or air core interface, that is a refraction point, and core cladding interface is a reflection. I already told that the N1 is greater than the N2. Where it is applicable is core cladding interface. This is you can see this diagram. Wait, this is you can see this particular area is core of your fiber material, and this above and below this a parameter of cladding. So you can see the N1 is refractive index, that is Ri profile of your core, and N2 is Ri profile of your cladding. So that is the first thing we have to know. And N naught, generally, previously I have told that N1 sin theta 1 equal to N2 sin theta 2. So when you are applying the Snell's law inside the core material or inside the fiber, the N1 is core and N2 is cladding. Suppose when you are applying the Snell's law in the wireless medium, the N1 is air medium and the N2 is the other coaxial cable or some other medium system. So that is the idea. But generally N0 they are taking N0 is always 1. So suppose if I am taking the source over here or optical source is here, the optical source is trying to insert my light into this core material. So that time it makes we have a reference angle, that is with respect to the axis of your fiber system. We have a reference line, so it makes an angle alpha like a theta, whatever it may be. So you can see here, this is the interface point between N1 and N2. This is N2 and this is N1. This is the interface point. You can see here the core cladding interface deals a parameter of reflection, and air core interface dealing the parameter of refraction. This is air and this is core. So from light inserting from gap to core, dealing the parameter of normally our refraction signal or our reflected signal, and core cladding interface deals a parameter of reflection. So already I told that based on the TAR principle, total internal reflection, we have to ensure that when I'm inserting any light into the core or fiber material, the light has to travel from starting point to the receiver or from the transmitter to the receiver. We have to ensure that the light signal is traveling inside the core. If the light is traveling from core to the cladding, we have to sincerely we have to think that the signal is lost. So we have to reconsider our fiber structure, and we have to reconsider our the design parameters of your core, and we have to think about how the materials which we have used for the manufacturing process of your fiber material. So put together we have to analyze. Then we have to test once again either the signal is transmitted in a core or in a cladding. So everything it is finalized or everything it is analyzed, then we have to go for the Pakka transmission system. If it is any error, definitely we have to think about our structure or maybe materials or our normal design characteristics. Everything we have to think. So that is idea about this system. Till now, if you have any question, please ask. Any questions? Please, if you have any question, please unmute yourself. We will at 1 minute we will stop here. Divagar, any question? Darshan, Divagar and Darshan.
No, no, sir.
Okay. We'll move to the next one, or okay, we'll move to the next idea. So this is the concept behind this ray theory and core cladding interface. And this is the main thing, important 2 mark question, Snell's law. Definitely you can expect first 2 mark or the second 2 mark, Snell's law. Define Snell's law. N1 sin theta 1 equal to N2 sin theta 2. That is the basic idea. You can see here, this is refraction, and this is grazing refraction, and this is reflection. So we have a three different three comparison system of refraction, and this is to TAR and also the reflection. You can see here N1 sin theta 1 equal to N2 sin theta 2. Theta 1 is incident angle. Theta here we are considering theta I. Theta 2 may be theta r. So n sin theta I, n1 sin theta I equal to n2 sin theta r. I is incident angle with respect to the normal line. Theta r is refracted angle with respect to the normal line. You can see this is blue line, this incident ray, and this brown ray or brown color denotes refracted ray. So normally we have a n1 and n2. So if theta r is less than or equal to 90 degree, definitely the n1 or the theta r should be definitely will be lesser than the or one value or a negligible value. So that time n1 sin theta I is less than or equal to n2. So when you are rearranging this equation, you can understand that sin theta I is equal less than or equal to n2 divided by n1. So from this you can analyze if you are knowing any one of the value. Suppose if you know the value of theta, definitely we know the value of theta I. Maybe we may not know the value of refractor signal at the time of incident angle. Definitely we will also calculate refractor angle with the help of inclination and also the difference between the incident and the refractor signal. But generally we know the angle with respect to the normal line, that is theta I. This incident angle definitely we know. Then n1 and n2 definitely we know. Based on these three characteristics, you can understand that sin theta I less than or equal to n2 divided by n1. This is one thing. And the grazing refraction, you can see here, this is theta r. I told that refracted signal. Suppose when the refracted signal is lies parallel or lies the same as of your interface line between n1 and n2, or it makes an angle of 90 degree. That is the important characteristics. If refracted signal, suppose when I am increasing this theta I automatically, suppose when I'm increasing theta I in this direction, automatically this particular refracted signal will comes down and it meters the one particular point like this. So if it is the case at that time, with respect to the normal line, this refracted angle will makes the angle is equal to 90 degree. So if it is the case, there is a grazing refraction, that is the TIR, basic TIR principle. So that time sin theta I is equal to n2 divided by n1. You can see the difference. The sin theta I here, the less than the n2 by n1, but whenever the angle with respect to the normal line, if the refractor ray makes a 90 degree, it is equal to sin theta I equal to n2 divided by n1. That is one thing. Already we have discussed the reflection. So n2 divided by n1 equal to, definitely we know that theta I will be equal to theta r. So a sin theta I is greater than the n2 divided by n1. So we have a three comparison. One case refraction, sin theta I is less than or equal to n2 divided by n1. Then if it is a reflection, the sin theta I is greater than the n2 divided by n1. That is the basic difference. If it is a refraction, less than; if it is a reflection, greater than. Okay, simple. If it is a grazing reflection, or if a refractor angle makes 90 degree, so that is sin theta I is equal to n2 divided by n1. Okay, clear? Any uh, question or any doubts? Any doubts or any? If it is no question, maybe we will move to the next answer. So this was Snell's law. Total internal reflection. When a ray is incident on the interface between, that is important, interface between two dielectrics of different refractive indices, that is RI profile. Here we have a glass and air. Glass and air, we have RI profile, N1 and N2. This is reflection and refraction occur. So when a ray is incident on the interface between the two different medium, where either reflection refraction will occur. So that is the principle of this concept. N1 sin theta 1 equal to N2 sin theta 2. So if they are asking in a university question paper or end semester question paper, define Snell's law, you have to deal particular this right information. The Snell's law deals a parameter N1 sin theta 1 equal to N2 sin theta 2. Okay. N1 RI profile of medium 1. N2 RI profile of medium 2. Okay. Theta 1 as angle of incident and theta 2 angle of refraction generally, or in terms of normally the refractor signal. So here you can see here this particular diagram, low index profile is N2, high index profile is N1. I told that you have to keep always N1 should be greater than the N2. So in this particular parameter, the N profile of air is 1, the N profile of glass is 1.33. So obviously we know that the glass is higher than the air medium. So I am making that the glass medium is N1 and the air medium is N2. Okay, clear. So you can see this is theta 1 is incident angle, theta 2 may be refracted angle. The plane which incident is plane that comprises of incident ray and also the plane to the normal line. So that is the idea of Snell's law. So n1 sin theta 1 equal to n2 sin theta 2. To understand this particular concept, you can see here this particular picture, the interface between the water and the air, the total image you can see here inside the or under the water or under the sea. So this is idea behind the Snell's law. So you have to ensure that n1 sin theta 1 equal to n2 sin theta 2. Always theta 1 is incident angle, theta r maybe a small r with a reflected signal is equal to 0, or theta I equal to theta r generally. So that is idea of Snell's law. So for the understanding purpose, I am making this picture. This is total internal reflection concept. So the interface point, you can see here, this is the interface point between the air and the water. Generally, for the particular example I am taking, here we have mentioned air and glass, but I am taking but air and the water. So you can see the entire image of the particular tortoise or whatever say turtle. You can see the inside your they are under the sea or under the water. So that is the concept behind for Snell's law concept. Any questions? Any question? Someone? Please unmute or okay. So that is Snell's law. And next we have a critical angle. You can see here, this is the idea behind the critical angle. If this is incident angle or incident ray theta I, and this is the refracted ray theta r. If refracted angle theta r is making 90 degree with respect to the normal line, that is critical angle. You can see here. So for n1 is greater than the n2, the angle of refraction theta 2 is always greater than the angle of incident, that is theta 1. Okay. When the angle of refraction theta 2 is 90 degree, already I have shown that the refracted ray emerges parallel to the interface between the medium. That is two interface, air and glass or air and the water. We have an interface system, that is this is the interface point between the two medium. Say for example, previous slide we have taken as air and glass. So same case I am taking here. So this is the interface point or interface line between the medium 1 and the medium 2. Medium 1 is glass, medium 2 is air. So if the refracted angle is making 90 degree with respect to the normal line, that is that time the theta I is equal to theta c, or theta I will be converted into the critical angle, that is theta c. You can see here theta I, we have a formula. You can see we have a formula, sin theta I equal to n2 divided by n1. Suppose theta I, this is theta I and this is the refracted angle theta r. If refracted angle is 90 degree, this particular theta I is considered as a theta c. That is this particular case. So sin theta c equal to n2 divided by n1. So this is the idea of critical angle. So what is the need of, or why we have to analyze the particular critical angle? If you are not analyzing critical angle theta c, or if we are going beyond the critical angle theta c, definitely this particular signal will not travel into the core. You have a issue or you have a loss. Definitely, if you are not satisfying theta c, definitely that particular time the signal will not travel into the core. Maybe that the signal is traveling to the core to the cladding. So that is the loss. So as I previously, one more thing I have to emphasize, one important thing. So theta c is important. If you are not dealing theta c properly, the signal is lost. So that is the idea behind the critical angle. So when the critical angle will occur, that is the important question. You can see here, this is incident angle. When I am changing this incident angle, definitely my refracted angle will comes parallel to the interface of between n1 and n2. That case, automatically whenever the theta r it reaches 90 degree, automatically my theta I is equal to theta c. So that is critical angle. So sin theta c equal to n2 divided by n1. I will stop here. If you have any question, please ask. Any questions? Reflected angle, and so I conclude. One second, I'll conclude here. Wait, I'll stop sharing. Okay, I am stop sharing. Okay, now I am making one small slide, empty slide. Maybe we can hear one by one. Okay. Any doubt, please?
Sir, when,
Yeah, yes. Who is this? Yeah, tell me.
Aparna, sir.
Yeah, tell me, Aparna.
Sir, when the incident angle becomes greater than the critical angle, it leads to reflection, right, sir?
One second, I will present my slide. Uh, wait. Please. We are speaking about critical angle or in a Snell's law?
Snell's law, sir.
Okay. Once again, I am presenting my screen. Maybe we can understand better. Can you see here? So this is the idea, okay?
Yes, sir.
Yeah, tell me, Aparna.
So when the incident angle is greater than critical angle, it leads to reflection, right, sir? So the information
Yes,
will be passed only in the core. It won't lead
yes,
to any
yes,
loss.
yes.
But you said previously when the incident angle is great, it becomes greater than critical angle, it leads to loss, and the information would be transmitted to cladding.
No, that is the thing. You have to understand that what are the things N1 and N2 you are considering. Generally, in a normal, suppose you have, you can see here, wait, you can, so the this particular slide, this is N0, N1, and N2. Okay, N0 is air medium. Here is air. Then this is the interface point between the air and the your core material. The core is N1 and cladding is N2. Okay. So for the particular case, if it is an incident angle deals a parameter with respect to the coaxial line or this or axis of center axis of your fiber material. So that time you have to see that N1 is always greater than the N2. So if it is the case, definitely the signal will get reflected to the inside the material or inside the core. But we have to ensure, as an engineer, we have to ensure that, suppose definitely as an engineer, we will not encourage the loss. So always we have to think about the signal has to be transmitted only inside the core. So how we can ensure that based on the incident angle and your reflected angle, that is theta small r and theta I. So whenever the theta I is equal to theta r, it is a parameter of total internal reflection. Okay. So when you will get the theta small r based on the theta r, if it is 90 degree, automatically you will not get the refraction, you will get only reflection. So that is the idea behind the Snell's law and your normal characteristics.
Yes, sir. Okay, sir.
Okay. So how you will achieve the refraction? By making critical angle, by making theta c. So when you are increasing either left hand side or right hand side by theta, you can see here, maybe from this diagram you can see, wait, so you can see here, suppose I am considering this theta I, when I am rotating either in upward direction or nearer to the interface point or nearer to the normal line. So automatically what will happen, I will get some diffraction in a refracted signal. So automatically when I am changing this theta I, automatically what will happen, my theta will lines are parallel to my interface point. So that time I will not get refraction, I will get only reflection, that is TAR principle. Clear?
Yes, sir.
Okay. Any other question? So this is the take-home point for today's section. We have discussed refractive, refractive index, and second point we have discussed Snell's law. Then we have a critical angle. So this is the take-home point for today's section or today's session. One is refractive index. What is a refractive and a reflective signal, and a Snell's law and the critical angle. So I will stop here. These are the three important take-home points of today's session. I will stop here. If you have any doubt, suppose any one of the student, if you have any doubt, please wait in answer. Maybe wait. You will answer. I will clarify the answer. Otherwise, I will take attendance. Maybe we will close this session today. One. Okay.
Sir.
Who is Abhishek? Abhishek, are you there, Abhishek?
Sir, I'm number 3, sir. Abhishek.
Okay, who is Abhishek?
He is number 2.
I think you are logged in two different points.
No, sir. Abhishek S is number 3, sir.
Okay, 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 okay. Oh, so two Abhishek. Okay. So 2, 3, 4, 5, 6. Who is number 6?
Discontinued, sir.
Discontinue. Okay, thank you. 7 இருக்காங்க. 8, 9, 103. Okay, 10, 11, 12, 13. Who is 13?